So now we are talking about an open domain question answering problem because we are talking about Wikipedia graph. So we go from very restricted paragraph to another paragraph and another paragraph. So simultaneously we are just doing retrieving and reading, but we are coupling them together so that it becomes robust. Because traditional methods just do retrieving, it is decoupled from the reading. But now it is fully coupled to get a robust answer with less error, with less susceptibility to something that creates some issues. And the open domain, you can think about, this is the usual pipeline. You have a question, you have a knowledge, external knowledge. First, you retrieve it. And we have only two modules, reader and retriever. So you think about this as zoom out, because you're retrieving from several books, from several documents. And reader, first, for example, you rank them and say, okay, this document is nice, but you should zoom in now. So now you're reading it. But then you understand, oh, this document was not good. You could choose another document so that when I zoom in here in this paragraph, I can find even better answer. So it's just a coupling of a retriever and a reader. So retriever and the reader have a coupling. So we train this and then train this. So iteratively we train both of them until it reaches a kind of convergence, a kind of semi-global solution. So in open domain question answering, the task is of answering a question given a large collection of text documents. And an answer is extracted by neural reading comprehension model. As you know, in multi-hop, we have just little lexical overlap, or let's say semantic relationship to the original question. And this is not working for long text or multi-hop question answering. If you have a question, how many, for example, have that, you put it to this approach of BERT. So you have question and say, what is your reference? I mean, which paragraph should I give this to this BERT? And then it learns, for example, says with this probability, this start and end is good. With this probability, this start and end, this is the answer with this probability. So we have softmax here, and you get this. But this problem has, because you only are allowed to, I think, 512 tokens to give this to make it more. But you cannot scale it in this way. Even if you scale it in this way, it's too expensive. And even it's still too expensive because it's very combinatorial. You don't know which document should I give here. And for example, loss of document 1 and loss of document 2. Loss of document 1 and loss of document n. So you should try all of these things. It becomes complicated when you have triples as well, or even more complex things. So it's not, I don't think this is a good approach to scale this problem. So what is a great solution? Again, this Iranian researcher in Washington University, great approach. This is a very great approach. But I think the cons of this, I'm not sure. I think maybe the embedding paragraph produces less semantic meaning. So it's not natural. Why not project into knowledge graph? And because it has its own complexity. So what is a sequential retrieval? Sequentially we retrieve each evidence documents that we read from Wikipedia. For example, this paragraph has a hyperlink to another paragraph. Then it is related to this. For example, this is related to other paragraphs. So the relationship is just hyperlink. And each node is just a paragraph in a Wikipedia graph. So, for example, here I want to say that there is a little lexical intersection between question, lexical overlap between the question and one of these texts. For example, paragraph 1 has 3 intersections. Paragraph 2 has just 1. So paragraph 2 has little intersection, and so the chatbot learns that founded and numbers should be in the same paragraph. When uses the question when. And this is the Wikipedia graph. We construct the Wikipedia paragraph graph using Wikipedia hyperlinks, as I said, and document structures to model the relationship between the paragraphs. So it's different from knowledge graph that each node is entity. Now each node is just a paragraph. And so we have a retriever. As I said, zoom out. There are lots of documents, lots of books, but in this. But when we zoom in, I mean the reader and retriever. In the reader, we zoom in. We have already found the paragraph. We want to know what is. Oh, I got the answer. This is the answer, for example, or this word is an answer. So we zoom in and we find the answer. And there is, as I said, there is a coupling, and because we want the answer to be robust, not just any answer. And about hard positive, I mean, it's obvious in the images. This girl is more similar to this girl, or this girl is not similar to this girl, so it's hard negative. You know this. So in the context of our problem, we have a graph-based recurrent retrieval, and we need to be trained, and we need to discriminate between relevant and irrelevant paragraph. For example, instead of saying this phrase is similar to this phrase, I want to say paragraph 1 is similar to paragraph 4, or paragraph 2 is not similar to paragraph 5. Because, for example, this is talking about computer science, this is talking about painting. And so we have the negative examples, and we use the negative examples to train. And the reasoning path is a sequence of paragraph. So we have when I say evidence, this is the path. For example, from paragraph 1, you go to paragraph 2 to paragraph 3. So you go to different paragraphs of the Wikipedia. And so the retrieval method learns to retrieve a set of reasoning paths in order to narrow down the search space. So it is sum of retrieval and the read. So we both of them, we want to maximize both of them. So for any question and any E, which is this path, we want to say which answer maximizes that, or which set of answer and path maximizes this objective. So each node is a paragraph from Wikipedia, and we use graph-based recurrent retrieval. Just a quick recap from recurrent neural networks. We have some output here, and there's some hidden states like H1, H2, and this is the update for both hidden and output. But here we only use the hidden states. We have a recurrent neural network, and we use BERT because, as I said in the previous lecture, I guess, it was the question, you give the question and the evidence that could be a paragraph, for example, paragraph 1. And you give the question, you give it to the BERT model, and then you get WI. WI is the answer. But of course, it's very heavy. That's why the article uses a kind of trick. So you have a question, you have a reference, which is your paragraph number 3, for example, or next time you give another question with another paragraph, because you already know the answer, because you have a pair of question and answer. You know the paragraph that corresponds to a specific answer. So we have a loss function in graph-based recurrent retrieval. And here, of course, the authors of the article they initialize it with TF-IDF approach, And so they have this sequence of GR. And we want to, this is our loss function. And finally, we have a sequence of paragraphs that if we just use the gradient descent, and then we can find the parameter and minimize this loss. So from a sequence, we just need to know which one is here best, because the best sequence, we want to pick that. And this is the answering reason, because if you find the best one that maximizes this path with given this question, then that's it. So this is the module of reasoning. So we had 2 modules. And this is Maryam Mirzakhani, the Iranian Fields medalist, the only woman in the world that has got Fields medal. So we should be patient and learn all paradigms, because the goal, I mean, my goal is to write an article to unify all of these methods, because to say, for example, which article uses which part in this framework. Because if you have a unified framework, you can combine different ideas, and you see all of their ideas are just one idea, but a different, let's say, implementation for each module. So you can think of your framework as having some modules, and each person implements it. For example, author 1, another author implements it in a different way.